Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In this course, in the last couple of classes, we have learned about the carbocation, we have learned about the carbon ion. I talk about the free radicals. I also talk about the carbene nitrines, and also in the last classes, I was talking about some of the important reaction for the radical chemistry, like the hydrogen atom transfer, then the halogen atom transfer. But in the today's class, I'm going to start with another reactive intermediates called benzyne or arynes. So I'm going to talk about how the benzynes are and arynes are can be formed from the starting from a different substrates. So let's first talk about some of the introductions. So I'm going to talk about about try to introduce you to the benzynes and try to do some sort of a comparison study with the acetylene. Then I'm going to talk about the different methods for the generation of benzyne. Okay. So first, if you think about a benzyne, which is or arynes, if you so in general this is a benzene ring. We all know that there are. Okay, so it is kind of a pi cloud in this benzene ring. We know about it, correct? So this is aromatic compound. So now what is happening once you go to benzyne. So you see in in case of one of the side, you will see one of these two carbon, there will be another extra bond. So it will get to some sort of it looks like a triple bond which is in a strained position. People can write also this structure as a plus minus. So we can use this type of Juita ionic structure of arynes when we try to explain some of the reactivity. Also there is another approach people use for writing as a diradical. As this is a formation of a bond, we can think about two radicals. So now if you try to think about the structure of benzyne, we know about the benzene structure, as I was telling you, it is forming so these three pi bond literally forming a pi cloud here. Now what is happening once there is formation of this extra bond. So this is the sp2 orbitals forming overlap. So this sp2 orbital and this sp2 orbital, they are forming overlap here and forming a weaker bonds. We call these bonds are weaker bonds which is formation happening. And if you think about this bond is not part of this aromatic system. Okay, so that's why this type of benzynes is also aromatic. But again the thing is this particular so triple bond like character, it is going to look like a triple bond, but there are some difference from a alkyne. And then these carbons where these bonds are formation happening, so you can see here these are sp hybridized. Okay, and also you can see there are strain energy about 63 kilocalorie. So that is the another important thing, that you are literally putting in a alkyne in a strain position. And we also going to learn about there you can see the frequency of this bond is 1846, which is kind of lower compared to a alkyne. Okay, if you think about alkyne, also the bond length compared to the normal alkyne, these bonds in case of arynes is weaker. You can see it's a longer longer bond length. And you can see from the carbon number values also there is a so these cases it is getting to even more desealed. Okay, and then the frequency, as I was mentioning, that in case of benzyne 1846, but normal alkyne going to comes around 2150. So you see that what is happening in case of benzyne, there is a triple bond like character, but it's a weaker triple bond. So that's why if it is a weaker bond, that means it is going to be much more reactive compared to alkyne. The other important factor is if you coming from alkyne, if you try to think about the molecular orbital, so there is a HOMO and there is a LUMO. So in case of benzyne, the LUMO energy getting decreased. So this is the LUMO energy which is coming down to, so it was 6.41 volt here, it is coming to now 1.33. So there is a stabilization of this pi star orbital here. As there is lower LUMO, so as the LUMO energy is lower in case of benzyne, now the nucleophile can able to access this LUMO, because nucleophile has to give electron density to the pi star orbital to form a bond, correct? So if the nucleophile have to approach here towards benzyne, to form this bond, it has to give electron density to the LUMO orbital. So that's so because of the lowering of the LUMO, now nucleophile, different type of nucleophile can access. I'm going to talk about different type of nucleophile, how they are forming bonds. Okay, But before I'm going to talk about them, I'm just going to talk about how these things was discovered. So in 1902, the initial discovery by Stoermer and then the Carl, they actually first proposed the existence of arynes. They mention about the existence of arine when they are trying to get starting from this 3-bromo benzofuran, they are able to get this 2-ethoxy benzofuran. So that time they mentioned that this might be going through some sort of a arynes intermediate. Then later on, it was Utik who also find out that once you start from the fluorobenzene using phenyl lithium, what is happening first there is a you can see this proton next to the fluorine, which is the more acidic one getting abstracted, formation of this corresponding lithium, and then there is a elimination happening to get to this type of plus minus or some sort of a benzyne species is going to form. Now once this forming a benzyne, so now the phenyl lithium is already present, correct, in the reaction. It's a nucleophile, so that can also attack here and then form the corresponding lithium, which can get protonated. So now you can think about that. So the benzyne, as you see that the first another experiment was done by John Roberts. So here the important thing is they started with the 14 level. So this carbon in the chlorobenzene, which is the ipso carbon, actually 14 leveled. Now in place of the potassium KNH2 potassium amide, what is happening here? It is actually going for the very similar things you have seen for the N-butyl lithium case. It is going to abstract this proton, which is the acidic proton, and going to form this benzyne. Now if the benzyne formation is happening, here the nucleophile is ammonia. So ammonia can attack from this side and it can attack from this side, because there is really no difference from attacking from these two sides. So that's how what is happening in the product, it can able to get to aniline where it is attached to the C14 carbon, or if you go to the other product where it is the next carbon, means it is the alpha and this is the beta, or the ortho carbon where the so it's a so this is kind of indicating that it is going through some sort of arine intermediate. From there the nucleophile can attack from the either side. As there is no preference, you will end up getting a 1-to-1 mixture of both the product. So in the today's class, my focus will be what are the different method how you can able to generate these arynes or benzyne. So we are going to learn about in different methods. So let's start with this method. As I was telling you, you have some aryl halide here, and you are using a strong base for a deprotonation, and then after that there is a elimination happening, which can generate the benzyne. We are going to talk about a method where you can also generate some sort of a aryl cation here. Then there will be proton abstraction and you can generate a aryne. Also there could be a fragmentation. We are going to talk about some of the fragmentation reaction where after the fragmentation this bond you are going to form a new bond here that is going to end up forming your arynes. Or there could be a Juiter ion. So if there is a formation of this plus minus, if you have a compound has a plus and has a minus, and then this one going to come back here and this is going to get out, we are going to talk about some of those reaction. And at the end I am going to also discuss some of the reaction using aryl radical. That if you have a halogen which can make a radical, then now there is two radical can form a bond which can end up making you benzyne. From a 1-2 substituted means if you have two groups here which can form a radical, if you have a X, if they can form radical and then they can form a bond, it can end up making a benzyne. So first example here using potassium terbutoxide in DMSO starting from the bromobenzene. So here what is happening, starting from the bromobenzene, this proton is the acidic proton is getting abstracted in presence of potassium terbutoxide, which is forming this symmetrical benzyne. As you can see, both sides can be equally getting attacked. And again in the medium you have the terbutanol, so that can attack from either from this side or from this side, correct, as I mentioned. So you end up getting both the products. Okay, so what is happening, this method is called elimination addition. First elimination happening of this bromine and then addition happening about the terbutanol. Again we are trying to show you the mechanism here. So I think once the terbutoxide taking this proton, it can form the benzyne. Now the attack path B or path A, it can give you actually it can end up getting the same product. Okay, but I think as long as this is a unsubstituted compound here, if your bromobenzene is substituted, Now you are going to see some difference in the selectivity. So now the question comes, as I was mentioning, that if your benzyne is unsymmetrical, which I was mentioning in the previous slide. So now you have to think about if the benzyne is unsymmetrical, now it is depending on what group is attached with the aromatic ring. If it is an electron withdrawing group or if it is electron donating group. So mostly you are going to see that there will be some sort of anion going to generate. Now based on the stability, you will see that different type of product will be, one will be major and one will be minor. So now if you think about, you have a R group here. Now if there is a benzyne here, the nucleophile can approach from this side or can approach from this side. Okay. So we are going to talk about that. If he is attacking from this side, what will be the preference, and if he is attacking from the other side, what will be the preference. So again, if you have a benzyne, so if you have R group here and benzyne is forming in this position, so now there could be attack from the para position or attack from the meta position. Okay. So we are going to discuss first with electron withdrawing. So as soon as if you have electron withdrawing group here which has a minus I effect, correct, we know about that group which have a minus I effect. Now once the nucleophile, once you have a, now the nucleophile can attack from this side. If it is attacking from this side, it is generating this anion here. So now this can get more stabilized because of the minus I effect of the electron withdrawing group. Comparatively, if you try to attack here in these cases, so that means in these cases this will be the meta attack will be, so this will give to the major product, but at the same time you will get some attack from this side. So that means your minor product, while you will see what is happening, your nucleophile will be here and you will generate anion here some sort of, and from there it can get protonated. So this will be your, so this will be your major, maybe close to the 70%, and that will be the minor close to 30%. Now the case is if you have a 4 substituted scenario, now there is a 2 possibility. It can go for a para attack versus meta attack. Now what is going to happen, if it is going for a para attack, it will generate a carbon ion here. If it is going for a meta attack, means attacking from this side, then it is generating carbon ion here. Now if you think about your electron withdrawing group have a minus I effect, correct. So the minus I effect means that will be going to stabilize more this carbon ion because it is close. This is a para position, this will be far. So if this the carbon ion which is forming here, so that can be stabilized more because this is in the meta position formation happening versus this negative carbon ion is forming in the para position. So it is far from this electron withdrawing group. So that's why this will be the major product here. Okay. Then now we are going to talk about the very similar scenario here. You have a CF3 group which is electron withdrawing, you have a chloro there. Now there is a possibility that first thing is going to be the sodamide going to abstract this proton, okay, to generate a minus which can eliminate this carbon, the chlorine, to form this corresponding benzyne. Now the nucleophile can attack, as I have already told you that in case of formation of a benzyne in the ortho position, your nucleophile is going to attack to the meta position to form to the this product as a major product. And now if it is in the para position, what is happening? The selectivity is not, you can still see there is 2 different possibility once this benzyne will form. So the one which is attacking from this side will be the major, the para attack will be major product, and the other one will be the minor product. So now we are talking about the other scenario where you have a methoxy group or you have a methyl group. So what will be the changes there? Now we all know that the OME group which have a minus I effect, correct? And you can see here the minus I effect will be the one which is going to be the controlling factor here. So because of this minus I effect, you have already seen that there will be, if you have a minus I effect, then the nucleophile always going to attack from this meta position, and that that will be the major product. But once you have a something like a methyl which have a plus I effect, in that case what is going to happen, you can see there will be you can see there will be the nucleophile can attack from this side, the ortho position, or it can attack from the meta position, correct. In both cases you will see not much selectivity, although we can expect the electronically it will be favored, that it is going to attack in the ortho position, because the negative charge should be generated far from the methyl group. But this will be sterically favor position, because if you are attacking in the ortho position, there is a steric effect happening between the methyl and the nucleophile. So that can be avoided if it is attacking from the meta position. So that's why you will see, based on the size of the nucleophile, sometimes you will not able to see mass selectivity difference. Okay. And in case of the force substituted one, as the charge will be forming really far from this group, so that's how you will see that, and then there is a steric and electronically both will be kind of not, there will be much difference in the product selectivity. Of course, if you have a nucleophile size is very much different, and based on that, sometime we have seen some selectivity, but not very much. So first thing, I'm going to start with the metal halogen exchange. That as I mentioned, if you have a halogen here, once you are generating this lithium, either through the metal halogen exchange, which I am showing here, just for the deprotonation. Then after, the next thing is elimination, going to generate the corresponding Benzyne. Starting from anthranilic acid, this is a very important method for generation of Benzyne. From starting from anthranilic acid, you can now use NaNO2HCl to form these diazo compounds N2 plus. So this diazonium chloride, in place of OH minus, it is going to abstract the acid proton. So now you can see you have this deuter ionic scenario here. You have this CO2 minus and N2 plus. So now once you are going to heat up, this CO2 going to get out from here. So you can see this can come back, this can generate an anion here, and now this can throw the N2 out. Okay, so there will be N2 and CO2 going to get out to generate a corresponding anion. Then the 1-amino benzotriazole. So starting from this 1-amino benzotriazole, using lead tetraacetate, it can also generate corresponding Benzyne. So what is happening in place of the lead tetraacetate? It is generating a nitrine here. As the nitrines are electron deficient, you might be familiar. I already talk about that before. So this lone pair, this nitrogen can give the lone pair to form this intermediate. From there, it can attack onto the other nitrogen, break this bond between these two nitrogen where nitrogen is the positive, form this benzotetrazine. And then this benzotetrazine, what is going to happen? Now there will be a fragmentation going to happen. This kind of fragment and generate a N2 minus and N2 plus, because one case it will be minus, one case there will be plus, and then there will be the N2 going to get out from here, and you are going to end up forming corresponding Benzyne. So this is a method of fragmentation, as I mentioned. So this is another method for fragmentation. So starting from this compound, you can see there is a triplet here, OTF, and there is this TBS protection. So once you have this TBS protection, and if you are using a cesium fluoride, it is going to attack on this silicon first. So once it is attacking on this, the F minus is attacking on it, what is going to happen now? It is going to form this, it is going to attack here, and once it is going to attack to the silicon in the here, now this can come back and it can allow this cleavage of this bond, and there is a triplet, is a very good leaving group, so that now it can the triplet going to get out, and then it is going to end up forming this corresponding Benzyne. So this is called some sort of a Groff fragmentation. Okay. So now you can see we have started from this particular compound, where you can see this is a trimethylsilyl phenyl iodonium triplet. If you have this iodonium triplet, what is happening, and you have this trimethylsilane here. Again, if you use this fluoride, I think I am going to also discuss these things in details when I talk about the silicon chemistry. So there is trimethyl group here. As the silicon having the vacant d orbital, you will see that the F minus going to attack on the silicon, and silicon fluorine bond is one of the stronger bond you are going to see. Okay. Now it is going to form this penta coordinated anionic complex, and then what is going to happen? It is going to break this bond, and it's going to get out as a iodobenzene to form this corresponding Benzyne in place of cesium fluoride. And there is another approach here. So this is a very important method. So it's a Kobayashi method for generation of arine. Again, so there is one carbon having the TMS, and the next carbon is with a triplet. So if you have triplet, we know the triplets are very good leaving group. So now if the F minus is attacking on the TMS, as I mentioned in the previous slide, you can write as a negative charge here, or write as some sort of anion here, which can come back here and get rid of triplet to get to the corresponding anion. So that means first it is going to fluorine going to attack to the TMS, then it is going to break this carbon and silicon bond. Okay, you can write in this something like in one shot, or you can write this way in the stepwise manner that can generate the benzyne. So this is a very important method used in a lot of times for generation of benzyne. The other method method using by Hoswa's method. So here you have a boronic ester instead of the silicon. Again borons are also electron deficient. So if you have a F minus, it can attack to the boron. So here instead of F minus you have T-butyl lithium. So again I think the lithiums are again a very good nucleophile, so it can attack to the corresponding boron to form this boronate complex, which you can see here. So boron having, we are going to discuss the formation of 8 complex in the when I am going to talk about the boron. But generally what you see, if you have so borons are generally trivalent, but if you increase the valence to tetravalent, then we generally call this type of complex as a 8 complex. So from there, once is forming the 8 complex, this carbon boron bond become weaker, so it can going to break, and you can write something like that, very similar to the silicon, going to form the benzyne, and the triplet is going to come out. So this is a another important approach. So I think this is a modification of the Kobayashi approach, where you don't need to use the fluoride. Here using cesium carbonate and 18 crown 6. Starting from this the TMS and the triplet can able to form the benzyne. What is happening here, the cesium is going to get to the into the 18 crown 6, and now the carbonate which is there, so the carbonate going to now attack to the TMS instead of the fluoride minus, the carbonate can attack to the TMS, and once the carbonate is going to attack, so once you see the nucleophile is attacking here, now this it can form the benzyne, and the triplet is going to get out, okay, to form the corresponding benzyne. The other method using the hexahydrodealsalder reaction. So what is happening, if you see there are 3 different alkyne here, this can participate in the 4+2 cycloaddition, and in the 4+2 cycloaddition this can form this corresponding benzyne. You can think about the very same reaction here, you have the alkyne, you have alkyne, so these 3 alkyne actually forming this cycloaddition. It's a hexahydrodealsalder reaction going to form the corresponding benzyne, which can further take part in various transformations. Another important work here, so using the 5-aryl thiothreone neomyl perchlorate. So this type of thiothreone molecule can act as a leaving group, thiothreone. So these are thiothreone molecules. So this thiothreone molecule can be synthesized starting from this compound, okay, using the trifluic acid and trifluoroacetic anhydride. If you take any type of aryl compound, it can go for some sort of a Friedel-Crafts reaction, and then it can form this type of compound. But the very important thing is these are very important leaving groups, so this can be used as an alternative to the halogens. So now if you have a halogens in your molecule, if you are using turbudoxide, so this has a better leaving group capacity, so it can leave your halogen there and at the same time forming a benzyne. So you can think about a advantage of this reaction, that it is leaving halogen, but it is taking this proton from here, and so this is acting as a better leaving group to form this corresponding benzyne. Then there is another method. If you start with this aniline here, where there is a terbutyl group in the C1 and in the C4 carbon, first thing is formation of this diazonium salt, and then once you go for the reflux, it is going to get rid of the N2 and it is going to form the corresponding benzyne. So the mechanism is given. First there is a formation of this diazonium chloride in presence of the turbudoxide in turbutyl ONO. So this is going to form the corresponding diazonium. Then there will be N2 going to get out, generation of carbocation. As you can see, there will be some sort of a, if you are using this corresponding acid, then there will be a, the counter anion, so which can able to go for a proton abstraction to get to the corresponding benzyne. Then as I mentioned that one of the other approach is the radical reaction under UV light. If you have 1,2-diiodobenzene, It can form the radical first. We have already mentioned it can first cleave this from the radical. Now it can either, so it can form a bond, so first, and then the next thing, it can form a radical here, and then both of the radical can go for a radical recombination to form this bond. Or you can also write that it can so what is going to happen, so it is going to get rid of the 2 I dot, which is going to form a I2. So in the today's class, I have I'm going to show you a summary that what are the different methods for the generation of arynes or benzyne. So first thing I talk about via the addition and elimination. So you can see here, first thing what is happening, there is a elimination happening. I think you can see there is a elimination of this bromine. So there is a base going to come back, take this proton, okay, anion, and then this can come back and get rid of this bromine. And then there is the metal halogen exchange. So if you have a metal halogen exchange, if you start with a dibromo compound, if you give some sort of Gigner, some sort of magnesium, it can form the corresponding Gigner reagent. Or if you go for metal halogen exchange, it will generate the corresponding lithium. Now it can form this benzyne. Starting from anthranilic acid, I talk about this, the formation of this deuterion. You have seen that. Then the fragmentation chemistry. We talk about from the iodinium triplet. Again, you have seen the cesium fluoride going to attack on the TMS, as I mentioned, and then there will be cleavage of this carbon silicon bond, and then there will be elimination of this IPH to form the benzyne. Okay, and then also I talk about the fluoride free activation, and then this hexahydrodyl solder reaction. And also I talk about some of some of the other method starting from these important compounds here, which has a better leaving capacity compared to the halides. And again from this, starting from this iodobenzene. Okay, so here are the references for this for this particular topic. And again thank you for coming to the class, and thank you so much, and I'm going to see you guys in the next class.